All right, now for the last talk for today, on this track at least, welcome with me, Henry, and the stage is yours.
A warm welcome from my side as well to this talk titled Taking a Bite at Apple's Network Stack, Reversing Proprietary Multi-Device Protocols with Log Queues. Before we get started, a quick note on myself. I'm currently a PhD student at the Hasso-Plattner Institute at the Jiska Claessens Chair on Mobile and Wireless Security. And besides that, I'm a fellow researcher at OpenCritis, where we publish information freely on the internet about European cybersecurity regulations and more specifically also German cybersecurity regulations. So when talking about reversing network protocols, especially in the Apple ecosystem, which I will be focusing on in today's talk, we can see that there's already quite a history of protocols, proprietary protocols that got opened up throughout the past years. So for instance, today we have OpenDrop as an open reimplementation of the AirDrop protocol, WatchSwitch, which brought support for Apple Watch, support on Android, OpenHaystack opening up the Find My network, and then there's a subset of features in the Apple ecosystem which is still pending reimplementations. And this set of features, so to say, is depending on a common link layer protocol. So to give you an example of what these features are about, suppose you have a Mac and an iPad. Then, for instance, with Sidecar Display, you can extend your Mac's display to an iPad. Or with Continuity Camera, if you own an iPhone, you can share your iPhone's camera feed to use it as a webcam on your Mac. And with Universal Control, you can control your iPad using the mouse and keyboard input that is connected to your Mac. And all these features rely on something that is called low latency Wi-Fi, a proprietary link layer protocol developed by Apple that serves real-time constraints and is mostly used for video and audio data. And at HBI, we've been reverse engineering this protocol and presented the results and the internals of low latency Wi-Fi and its low latency mechanisms last year in December at the 39C3. And if you're interested in the specifics of low latency Wi-Fi, feel free to take a look at my talk that I held back in December 2025. Today, however, we are going to talk about the tooling that brought us to the insights I presented back at Chaos Communication Congress. A common challenge when it comes to reversing proprietary systems and also proprietary network protocols is that you can investigate a lot of different log sources. And each log source will give you a unique perspective on the system you are investigating. However, when it comes to getting a holistic view, this is of course very complex. So you can, for instance, analyze system logs, kernel traces for kernel space activities, packet captures in order to investigate network level activities on certain interfaces. But what was missing in the past was a tool that consolidates different files and different file formats into a single, holistic, unified timeline that displays all events as they happen in a timely manner on both devices, which is, of course, another challenge in network protocol reverse engineering, as a lot of things happen concurrently on different systems. There are, of course, tools that already handle such tasks about log aggregation. However, stacks like the ALK stack or the LGTM stack are lacking crucial features that are important when it comes to reversing network protocols in multi-device setups. So for instance, especially in the Apple ecosystem, there are limited log collection capabilities when it comes to iDevices. These stacks also do not account for clock drifting effects, as far as I can tell, and also they are not tailored to reverse engineering and do not support reverse engineers in transitioning from dynamic analysis when looking at system logs to static reverse engineering in order to continue the reverse engineering journey in tools like Ghidra or Binary Ninja. So the answer to tackle these challenges is LogView's toolkit. LogView's toolkit offers 4 components that tackle these challenges. And before I go into the technical details of the LogView's toolkit, let me give you some examples of what you can do with LogView's toolkit. So suppose you have a log file that contains all of the aggregated information you captured during your network protocol, for instance. Then you can see, for instance, in the example of sidecar display, that the Mac Mini has posted its peer presence on low latency Wi-Fi's interface LLW0, and that the iPad is then setting the link state of LLW0 to up, that there are certain low latency Wi-Fi parameters enabled, and also in the system logs somehow configured. And later on, you could see that on the Mac Mini, there appears to be some network activity on this very interface. Another example I have from my reverse engineering journey of low latency Wi-Fi is that LogView's toolkit enables you to correlate certain system call purposes with network activities. So in this example here, we have the system call channel sync, and it appears to be accountable for network activity appearing on low latency Wi-Fi's interface. And of course, with LogView's toolkit, you can verify that as it appears throughout the entire capture. Now, when we talk about log aggregation, we of course also need to talk about collecting these logs, especially in multi-device setups. And the 2 components in LogView's toolkit are LogView's collect and LogView's sync that are responsible for that. So suppose you want to capture your network protocol, then what you would do is instantiate and initiate LogView's collect. And it then prompts you to indicate that you are about to start the network protocol you want to analyze. So you just hit I. It starts the captures on the interfaces, for instance, and also starts kernel tracing. And then you can connect, for instance, in sidecar display to your iPad. It will start capturing network activity. Then you terminate your network protocol, and LogView's toolkit will then automatically pursue and aggregate the logs you want to analyze further on. And in the file system then, there appears a file in pcap-ng format, for example, that you can analyze in the next steps. When it comes to log sources, the LogView's toolkit currently supports 6 input sources. One is, of course, console, or its equivalent, the log utility on the command line, which enables you to collect certain system logs on iOS and macOS. Of course, Wireshark and Packet Logger for capturing network packets and Bluetooth activities. CC-tool output, which is Apple's proprietary framework for capturing all kinds of logs that are related to network-related tasks. And dtrace and ktrace for kernel tracing the kernel space. Now, during the development of LogView's toolkit, we were able to bring support for CC-tool on iOS, and also found out that ktrace support is also already open source. However, it's buried in very complex directories in the open internet, on GitHub, on Apple's open source repositories. And LogView's toolkit now documents how to bring kernel spacing, kernel tracing support to iOS, so that we have 11 out of 12 tools that are both available on macOS and iOS for collecting logs. When we speak about multi-device setups, we of course also need to talk about how to orchestrate the collection across different devices. LogView's toolkit solves this by serving the user a command line interface with logacquisition.sh, or as we just saw, LogView's collect, which is just a wrapper around this shell script. And for one, it initiates the capturing on the macOS device, but also instructs the iOS device to invoke the commands that are required on the iDevice itself. Multi-device setups also require us to think about clock offsets and clock drifting effects, since in multi-device setups, there are always clocks involved that are not perfectly in sync. And with output of k-trace, which is a volume of multiple million tracing events per second, this is of course mandatory, because otherwise the events will end up being misaligned in the aggregated log file. LogView's collect solves this by implementing an NTP client and an NTP server that is running during the log collection. And these clock offsets that are calculated using NTP are then used during log aggregation in order to end up with a correctly aligned log aggregation file. And this brings us to aggregating logs with LogViews, which is the component LogViews in the toolkit that takes different kinds of files, parses them into business logic, and before outputting a file, the user is able to provide certain pre-recorded noise for noise reference so that only the relevant data to the protocol ends up in the final file. The user is also able to provide static filter criteria. And finally, the LogViews toolkit outputs a pcap.ng file or a log archive file for further analysis. Now, the LogViews toolkit also provides one very interesting feature, which is that it's capable of resolving certain log event messages to certain and very specific user and kernel space functions. And LogView's context is responsible for that, which we call backtrace reconstruction. So just to give you an example of what I specifically mean by backtrace reconstruction, suppose you have your aggregated log file and now see this very event message, which says something about enabling HPP low latency Wi-Fi parameters. And now using static reverse engineering, you want to know what is specifically happening when the systems reach that exact point. So what LogView's context is giving you is a list of possible functions that could have emitted this log message so that you can continue your static reverse engineering in Binary Ninja or Ghidra. Backtrace reconstruction is currently supported in both console and k-trace output. And to start explaining what is happening at a technical detail, let me focus on console at first. So suppose you have opened up a log archive file in the console application. Then what you are seeing is basically an event message, maybe also the process that is emitting the message. But what you can also do is take the log command on the command line utility, and it will give you more fields that are not visible in the console application. And the key field here is the format string, because format strings are appearing in log archive files and also in binaries you are interested in. So format strings at this point are the missing link to transition from an event message to a certain function where you can start your static reverse engineering. So in the case I just showed earlier, you could now go into configure HPP low latency Wi-Fi parameters in the case of our event message and take a look at the binary and the function and investigate what low latency Wi-Fi is doing there. And during our analysis, this really helped us in discovering what low latency Wi-Fi is about, because this function invokes another function called set low latency Wi-Fi parameters, just to give you an example. So on a high level, you need, of course, know at first your interesting binaries, the binaries you are interested in. Take that, give it to logview's context, let it being analyzed, and logview's context will then give you a mapping file from strings to functions. So just another example. Suppose you have loaded the driver kit shared cache into Binary Ninja, which is basically a data structure that contains a lot of frameworks related to drivers and network-related tasks. And you already experienced that this contains certain symbols related to low latency Wi-Fi. Then what you could do is just invoke logview's context, and it will give you a command that you can paste into the Binary Ninja script editor. Logview's context will then output a string mapping file. So just to give you an example, enabling HPP low latency Wi-Fi parameters is in there and is mapped to the functions. And this mapping file can then be used during log aggregation in order to tag the logs you are interested in of the binary of your interest. Another very useful utility for backtrace reconstruction is ktrace. Because ktrace, as you can see, is emitting a lot of volume during log collection, multiple millions per second. And one very interesting thing about ktrace events is that they are based on so-called debug identifiers. Debug identifiers are given to a function called kernel debug. And kernel debug calls and their debug identifiers are somewhat unique to the functions that invoke the kernel debug function using the debug identifiers. So this basically gives you a mapping again from ktrace events to function names in the kernel space. So the idea here again is that given the high density of ktrace events, you can gain a rough backtrace based on these debug identifiers. And the procedure here is similar. You just take a kernel cache, analyze it with logview's context. It will then give you a mapping file. So in this case, you can see that certain kernel functions using network interfaces are also using debug identifiers. And logview's context will then tag these kernel traces with the function names in the kernel, but also in other binaries that are using kernel debug calls. Logview's toolkit, in summary, is therefore not only a pure log aggregation toolkit, but it also is a toolkit for collecting logs in multi-device setups. It supports currently more than 6 input formats. It's basically extensible to any tracing tool. Takes account of clock offset correction and noise filtering, and also supports you in transitioning from dynamic analysis to static analysis using backtrace reconstruction. And finally, logview's toolkit supports output in log archive file and pcap-ng format. We are releasing logview's toolkit in the version 0.2 with more stability improvements, support for backtrace reconstruction, and more setup enhancements later this week. And logview's toolkit is already available on codeberg.org. Finally, I would like to thank the NLNet Foundation for providing funding for this project, as it really helps us to develop reverse engineering tooling that is incredibly helpful in order to open up proprietary protocols that are currently gated in walled gardens. Thank you.
All right, thank you very much. Are there any questions? Yes?
I think you talked about it, but I was more interested in the clock drifting. So you had the NTP client server,
Yeah.
but in practice, so you can run the MTP at the same time you capture and doesn't have an influence. Like it can get to like granular enough the precision that it doesn't influence the rest, right?
Yes, not to my knowledge, at least. As you can see, this is still an NTP implementation. There are better protocols like the precision time protocol. We currently don't have support for that, as it, I think, requires also hardware support and is more complex than NTP. But currently, we are in the range of a few milliseconds. So this could be further enhanced using PTP. Yeah.
Thank you for the talk. I am very curious about the backtrace reconstruction you presented. And I was wondering if this is something that could scale to processing an entire DYLD shared cache at once, and then maybe that could be also something that we could automate and have this run for new iOS releases and just publish the mappings, and then we don't have to do it ourselves every time?
Yeah, that's a very good question. I haven't tried to map the entire DYLD shared cache, but it's definitely a thing I plan to do. And I would also consider putting this mapping file then into the public version of LogView's toolkit. Performance-wise, we have to see, but I think it should be feasible.
Cool, great, thank you. Looking forward.